Thank you for having me here, at least virtually. So yeah, I'm going to talk about some deterministic eco-evolutionary models and how to try to incorporate when you have like multimodal trait distributions and the feedback with ecology and evolution. So this talk will cover some material that originates in a paper by Akira Sasaki and Stickman back in 2011. And we did some more recent work on this in collaboration with Akira Sasaki and Mike Boots in a paper that is currently in press, but there's also a preprint of bioRxiv. So basically it will cover materials from these two papers. So like a basic question in evolutionary ecology is how do ecological processes affect how trait distributions change over time? So basically, one way to handle that is in quantitative genetics, for instance, is to assume that you have a normal trait distribution. You can do a lot of things if you assume that the distribution is and stay normal over the course of the dynamics. And there's another approach that considers that if you assume that like the variance is a proportional to is a scaled by a parameter epsilon, and you make this epsilon small, then the distribution becomes narrow and clustered around the mean of the population. And then in this under this weak selection or small variance approximation, you can actually write equations for the dynamics of, like, for instance, the density of focal population and the mean trait of in the population, and possibly over moments like the variance and so on. But I will, for now, we'll focus on this too. And basically, you have two coupled equations between with the ecological variable, which is the density of the population, and the evolutionary variable, which is the mean trait in the population. We have some, and we can tailor expand the dynamics to have some first order term here and here. Okay, and what is the meaning of that? Is that you have a separation of time scale between the ecological process and the evolutionary process. Basically, this phi function here captures the ecological dynamics, and the evolutionary dynamics is captured by this product of the variance in the population, variance of the trait distribution, and selection gradient. If this variance is small, then the mean trait is going to be a slow variable, while the population density is going to be a fast variable. And so under this this condition, we can use what is frequently done in evolutionary ecology, some quasi-equilibrium approximation. So this means that on the slow time scale, the mean trait changes subject to a certain constraint that we can derive, and we obtain on the slow time scale kind of closed equation for the dynamics on the mean trait. It's not closed because it depends on the variance in the population. We can also derive equations for the variance and other moments, so it's not necessarily a problem as such. Like a short application of this is like very classical model of character displacement, where you have so basically you have the population growth rate for individuals with trait Z is going to be given by this function. I will come back on the meaning of this E later, but for now, let's just say it's a function of Z of the trait. We have a kind of fecundity or fitness term, a rho, and we have the competition terms that depends on basically A is a kernel that gives the intensity of competition over individuals with trait Z experienced by from individuals with trait Y. And we can, if we assume again that this trait distribution is clustered around the mean, we can make a tailored approximation of this competition term. And in that case, we obtain a very simple dynamical system where the dynamics of the total population depends on the mean trait of the population. Dynamics of the mean trait depends on the variance of the mean trait and on the population. So we have a feedback of the ecological variable on the density, on the dynamics of the evolutionary variable. And we can also calculate the dynamics of the variance. And I will come back to how we can do that later, but it's just for illustrative purpose right now. Okay, so we have our phi function, our selection gradient. And basically what I want to illustrate here is that if we do perform simulations of this model, or even do like full simulation without this Taylor approximation, what we observe is that in a kind of phase plot where we have the ecological variable on the y-axis, the population density, and the evolutionary variable on the x-axis. So as the mean trait, we have this very fast change of the ecological variable that converges to manifold, where then the mean trait evolves more slowly while staying on this relationship here. And this kind of brush of time scale with first a fast relaxation of the ecological variables, and then slower change in the evolutionary variable is something that we often find in models of ecology, because basically they always often we use this kind of weak selection, small variance approximation. Okay, but so what are my intention with this introduction is to briefly illustrate that for narrow unimodal trait distributions in unstructured populations, we have a good idea of how to proceed, because a lot of the frameworks we have, like quantitative genetics and quantitative genetics, sometimes only use the Gaussian approximation. But let's say in general, if we want to have frequency dependence, a lot of the quantitative genetics or dynamics approaches use this idea that we have a kind of weak selection, so either a small variance or like a mutant that is closely resident, which amounts to the same idea. So what I want to do in this talk is to examine how this picture is altered by two complications. First, what happens when you have a multimodal trait distribution, so maybe distributions with two or more peaks, and what happens when you have a population structure. So I'll start with a kind of the idea of what happens when you have several peaks, and how does it affect this several time scales that we talked about. And more specifically, is it useful to understand like processes like fast evolution, which is a very popular theme right now in evolutionary ecology and ecology. So to formalize this a bit, so let's start with some densities. So let's nzt be the density of individuals with trait Z at time t. Okay, and with a slight abuse of notation, I will call NT the total density of individuals at time t. So basically the average of nzt over z. And from these two quantities, we're going to define the trait distribution, which is the frequency of individuals that have trait z at time t, which is this quantity phi zt here. So our aim is to understand the joint eco-evo dynamics of nt and phi zt. Okay. So like classical quantitative index models will assume normal trait distribution, and often the constraints are that this normal distribution stays normal. But so if you want to capture things like the fact that you can have disruptive selection that creates multimodal distributions, like is frequently observed in trait distribution nature, where we have skewed distributions on multimodal distribution, a bit like this very nice picture here, then you may need to you need something else. And one of the idea that Sasaki and Dickman introduced in that paper was to use this kind of multimodal decomposition, where you write the distribution at the population level as a mixture of morph distributions. So it's the sum over all morph. We have m morph here. So like say here, a morph would be maybe this one peak here would be one morph, maybe this other peak would be another morph. we have some flexibility on how we define morph. We could also imagine that there's a third morph here with zero frequency. But let's say we say that in this bimodal distribution, we're going to model it with two morph. We'll just write the distribution as the sum of morph distributions phi I, weighted by the frequency of morph I. So the frequencies will give us the height of the different peaks in the distribution. We can also, I just hasten to say that we can also do all the approach, and assuming that we have like maybe two overlapping morph distributions, like maybe what we would have in mind if we assume like want to know how we start with two morphs that are very close and how disruptive selection will move peaks apart. We can start with simulations where we have two overlapping distributions. But okay, this is our starting point. And so basically, if we want to show it graphically, when you have two morph, we just decompose this distribution into two morph distributions in blue and yellow, and this distribution will have moments that we're going to be interested in. So if we look at the moments of the trait distribution, we have population level moments, like the moment of the distribution phi. That would be like Z bar will be the mean trait value at time t, the V will be the trait variance at time t, maybe we'll have t would be the third central moment of time t, and we can do the same for the morph distributions phi I. And typically, we're going to consider symmetric morph distributions. So maybe actually even in most of what I'm going to do later, I'm going to assume that the morph distributions are Gaussian, like in classical quantitative genetics. But of course, the whole distribution is not necessarily Gaussian, especially if we have two peaks, and it's not necessarily symmetric because, like in this distribution here, it's not symmetric either. But at the morph level, I'm going to assume basically symmetric trait distribution, so that this Ti will be 0, but the T at the population level won't be 0. Okay, and so we can, with this approach, we're going to derive, as very classically done, it's been done for a long time, this kind of moment approach to modeling evolutionary change. You can go back to papers of Henri and Burton and others. It's a very classical approach. The difference here is that instead of doing it at population level, we're going to do it at the morph level and then couple all these morph equations together. And if at the morph level we apply some kind of suitable moment closure approximation, for instance, the Gaussian closure, assuming that each morph distribution is a Gaussian distribution, we can characterize a morph at time t by its relative abundance. That's the frequency FIT of the morph. Its positions, that's the morph mean, okay, Z bar I, or its widths, which will be the morph standard deviation. Okay, and so that can be like these three characteristics of morph can be enough to describe the dynamics. That's at least the gambit we make. And so, as I said, in this talk, I will simply assume a Gaussian closure at the morph level to simplify things, but you can imagine other moment closure approximations if you wish. So now we have some statistics to describe the state of the population at a given time, and now we want to understand the dynamics of this population. So we want to understand how the various peaks of the multimodal distribution will move and change over time. Now maybe we start with this kind of very peak distribution, and then there's maybe directional selection that's going to shift the peak toward the right, and then maybe we'll have some disruptive selections going to flatten the distribution, and we end up with two peaks, and then there's the stabilizing selection that is going to maintain these two peaks in the distribution. And so that's basically, I've described disruptive evolutionary branching here. Starting with one peak, we end up with a bimodal trait distribution. And this is the kind of I think that the approach can model easily. So if we start with at the population level, we can describe change the density NZT by the PDE, where we have like a selection term that depends on the per capita growth rate of individuals with trait Z, and this per capita growth rate will depend on the trait and on the environmental feedback. So anything that we need to calculate this R really, so it can be maybe N, like N would be density capture dependence. That can be the whole frequencies of the different morph, as we will see, or the more specifically at that stage, that can be the distribution phi zt. Can be resource densities, like maybe the density of resource that the consumer when looking at is consuming, or maybe the density of susceptible hosts if we're interested in pathogen evolution. It be anything we need to compute this, like the reproduction and survival of the focal species. So this is on selection term, and there'll be a mutation term too. But first, I will only focus on the selection term so that we can understand this. And of course, this equation may need to be coupled to some other equation, like I said, the density of resource or susceptible host or anything. So let's do this small morph variance approximation. So if I assume that the morph distributions are tightly clustered around the mean, so that we have some kind of narrow peaks in our distribution, and we define this xi quantity as the z minus z bar I, so the deviation compared to the morph mean, and we assume that this small size is order epsilon, where epsilon is a small parameter. If we make a Taylor expansion of the vital rates around the morph mean, like this very standard Taylor approximation, we can use this to actually derive equation for the dynamics of the total density, the morph frequencies, FIT, so that's the height of the peaks, the morph means, Z bar IT, so that's the positions of the peaks, and the morph variances, VIT, will give us an idea of the width of the peaks. And this is what the general system of equations will look like. We'll have some equation for the total density, then for the frequencies of the different morphs. Then a density for each of the morph, we'll have equations for the morph mean and the morph variance. And here I've used the Gaussian approximation at the morph level, which means that this is where the VI square terms comes from. Otherwise, we'll have a fourth order moment that will pop up here. So basically, as you can see that we just look at the leading order terms for each of these equations, and like the total density, the dynamics of the total density will depend on the means of each morph, and on the frequency of the morph. The dynamics of the frequency will also depend on the morph means and the frequencies. And the dynamics of the morph mean will depend on the variance and on kind of selection gradient at the morph level, and rather more specific selection gradient. And the dynamics of the variance will depend on the square of the variance times something that measures the curvature of the fitness functions, if you wish. Importantly, now we'll stress this later, these functions are it still depends on the environment, so it can depend on the other morphs, it can depend on the total density, on the density of a resource, so we still have frequency and density dependence. These morphs are not independent, all the equations are coupled. So now we have that. One thing we can see is that these two equations here are scaled by the variance, so that means that we have, if the more variances are, we say order epsilon square, it means that these two equations, this system of equations here is a system for dynamics for the fast variables, and then we have dynamics of the slow variables here. So we have again a separation of time scale, where the frequencies and morph and density of the population are fast variables, and the morph means and and more variance. So the moments of the trait distribution are slow variables, and we can use that to make progress if we wish. One thing I want to stress in this talk is how we can use that to understand the kind of coupling between fast and slow evolution processes. So if we, instead of looking at the morph mean Z bar I, we look at the population level mean trait. So Z bar, so the mean trait at the population level. It's very easy to compute. It's the sum of I of the frequency, of the morph means weighted by the frequency of each morph. And so the dynamics can be written as like this, when we have a first term that depends on the change in frequency, so it depends on the changes in the peak heights, if we wish, and a second term depends on the changes of the morph mean, so it means how on the changes of the positions of the peaks of our multimodal distribution. And so if we have two morphs, for instance, like a wild type and a mutant, we obtain these following equations, where in blue we have everything that comes from this blue term here, and in green everything that comes from this green term here. And this is how this looks like. So the change in the mean trait at the population level is depends on the difference between the mean traits of the two morphs, like M and W. Then something that looks like a standard variance in population genetics, like the frequency of the mutant times the frequencies of the wild type, or FM times 1 minus FM. And then the delta R is a kind of first order approximation of the difference in growth rates of for the one morph compared to the other. And then this green term here is kind of an average weighted by the morph frequencies of the selection gradients of each morph. So it depends on the variance of morph I and the derivative of the fitness function evaluated near the morph mean. Why is this useful? I'm going to just repeat this equation here. It's useful because if we look at this two limit cases, first case is if we assume that this difference in morph means Z bar M minus Z bar W is large compared to the morph variances, which are assumed to be small, then the two morphs are very different. So the two peaks of the multimodal distributions are apart. And so it corresponds to strong selection. And the first line in this case will dominate, and we have fast evolution. It's like population genetics, where everything is driven by the change in variance. And so we have something that is, we have a variance, population genetics variance, FM times 1 minus FM, multiplied by the selection coefficient, which is given by the difference in growth rates between the two morphs. But if the two morphs are very similar, so these two morph means are very close, then maybe this second line is going to dominate. In this case, we're going to have a slow evolution, like in active dynamics and sometimes in quantitative genetics, where the rate of evolution is scaled by the morph variances and driven by selection gradients, which are the derivative of fitness function evaluated at the morph mean. And so we can couple actually the fast and slow evolution process with this approach. And I'm going to illustrate this with an application with in a model of pathogen virulence. We have some susceptible hosts that can be infected and they can become infected. And I'm going to look at the evolution of this virulence trait alpha. And so if we do our formalism, our alpha is going to be, our fitness function is going to be beta alpha times S minus D plus alpha. So that's the standard growth rate of in a SIR model. We have this trade-off in transmission virulence, and I'm going to show simulations where we start with a high density of susceptible host, a low density of infected hosts, so we have an epidemic phase, and start with different distributions of virulence. So these are the equations using this general framework. We have again the blue term here in the first line, the green terms in the second line. So again, just to recap, two limit cases. Either the morph variances are very small, and this difference here is not too small, and then basically selection favor morph with the largest growth rate, a bit like R selection, if you wish. Oh, we have weak selections. So, these two morphs are actually close together, so the peaks are overlapping, and then we are going to have a slow evolution of the trait, let's say alpha bar, in the direction that is given by these selection gradients, which can be approximately the same, and we end up with an evolution endpoint which is given by this equation. So we maximize R naught in that case. So I don't want to go into detail, but then we have two little cases. One where I'm maximizing R, basically the growth rate, and the other where we're maximizing R naught. And so it's a bit like, when for those familiar with this, it's a bit like case selection. And if we do kind of simulations of this, like if we start with a distribution with two overlapping peaks, okay, and so the variance in population is quite small. And the kind of dynamics we have, if we plot here, we have the density of susceptible hosts, and here we have the mean virulence. We have here a very clear separation of time scale where we converge first to this manifold, and then we have a slow evolution of alpha. We can show here this in the dynamics, where you have quickly we settle on an ecological equilibrium here, and alpha bar, the mean virulence, is not changing that much. And if we look at the longer time scale, we see that we're slowly going to this red line, which corresponds to this red dot, which is the maximization of R naught in that case. And we have a and the equilibrium tracks this slow change very gradually. This is the case where we have a unimodal distribution. So that's the theory I presented. But now if we have two peaks, then we can see that we still have this separation of time scale, but it's not as clear cut as before. But it's still a good approximation, even though the variance at the population level is much higher. But then if we look at, again, a stronger selection with two very different morphs, we have a very complete different picture where basically the phase portrait is very different. And what happens is that we first have selection for highly virulent strain of the pathogen, and then this strain becomes selected, and we go below the potential ESS of our system, and we need to look at a longer time scale to see that gradually we're going to come back to this equilibrium at point on the slow time scale. So basically here all this phase here captures kind of fast evolution regime where the change in frequencies of the different morphs occurs on the same time scale as the change in the dynamics of the ecological variable. So that's one application of this multi-morph formalism. Okay, so what about population structure? Do I have time? Yeah, I did, maybe not that much. Okay, so what happens with population structure? Well, it's the same, but it's more complicated because now we have k classes of individuals. So we have to introduce new notations. So we have densities of individuals with trait Z in class K, and KZT. Then the total density of individuals in class K at time T will be NKT. That's basically the same we had previously, but we need to specify what's happening in each class of individuals. And then we can also average over our sum over all classes to obtain the total density at time T. And then distributions, we have also distribution, but we have two types of distribution. Now that is the class distribution, that is the frequency of each class, so the fraction of individuals that are in class K at time T. And we have then trait distributions, which are going to give us the trait distribution within one class. Phi k z t is the trait distribution in class K, and there's also an overall trait distribution if we average over all classes with this formula. So we have more notational clutter, a bit more higher dimension system, but we can do the same as we did before. And with each class, we're going to do a multi-morph decomposition. So we need to decompose the distribution of the trait within class K as a mixture of morph distributions weighted by the frequency of morph I in class K, which is noted Fik. So the notation I'm going to use here is all the morph related notation are subscripts, and all the class related notations are superscripts. I find it helpful, but some people may disagree. Okay, so basically, if we graphically put that in the picture, we have one morph distribution in class A. We can decompose as before this distribution to like maybe here 2 morphs, and we have another distribution of the trait in class B. Not that they're not necessarily the same. We allow for some differences in trait distributions in different classes, but again, we can do a morph decomposition, and then we have dynamics that we need to deal with. So as before, we need to know some fitness functions, but now we need to know the transition rates Jk that from class K to class J for individuals with trait Z. And we're going to collect this in a matrix RZ. Again, I'm going to drop the dependency on E here, but keep in mind that this matrix will depend on the density of resources or densities or anything. And we can do the small variance approximation. So within each class, we're going to assume that the morph distributions are clustered around their means. So this means that this quantity here is small. We do the same Taylor expansion as before, except that so Jk, so the means give us let's say the reproduction of K individuals into class J. So we're going to do a Taylor expansion around the morph mean in class K inside the parental class, so to speak. So this is the crux of the approximation. And again, we're going to use that to derive equations for the dynamics of the total densities, morph frequencies, morph means, morph variances. So the dynamics of the densities can be written in matrix form, very classical form for class structure populations in population dynamics. The only difference here is that the matrix R bar is the matrix of average vital rates. Okay, so it's the average of all morphs. And we can approximate this to first order in terms of the morph means and the morph frequencies. We can write an equation for dynamics of the morph frequencies. Again, they only depend on the morph means and the morph frequencies, and it's basically a class structured version of the replicator equation. This is can be the mean growth rate, and this is the growth rate of morph I, and we need to average over all classes. I don't want to go too much into the detail. We can chat about this later. We can go to the paper. I just want to explain the basic ingredients. So there's some subtleties because there are different ways to calculate the morph frequency. And so it's also useful to use the global frequency of morph I. So that's the average frequency of morph I over all classes. And this morph frequency is UIK. It's basically it's the fraction of class K individuals among all morph I individuals, whereas Fik is the fraction of morph I individuals among all class K individuals. That's slightly different. But the reason for introducing these U variables is that they're going to be useful later. And why is that so? Is because we can basically a class, we can define, assign a quantity and a quality to a class from the point of view of a focal individual. And these U morph frequencies they represent the quantity of the class. Like they say how much if I take morph I individuals, is it likely? What is the chance it is going to be in class K, for instance? So we have some dynamical equations for this vector of morph frequencies. Okay, I'm going to speed up a bit, but basically we have this dynamical equation depends on the matrix of more specific average rates. Okay, that's the same as before, but at the morph level. And this is the per capita growth rate of the morph I, so the average growth rate of morph I for the specific morph I. This is one dynamic equation. And there's a kind of adjoint equation that gives us the dynamics of vector V, which is this, and this is the vector of individual repetitive values for a specific morph. And it's going to be a measure of class quality because we're going to represent the contribution of a certain class to the future of a certain morph. And the reason for introducing this is that we can use this repetitive value to obtain a lower dimensional approximation of the dynamics. So we can, skipping the details, we can obtain some dynamics for the morph means and for the morph variances. So the morph means have this form. We recognize in red this kind of selection gradient like classical quantitative genetics selection gradient expression with the variance time derivative. But we have another term that represents the kind of migration between two classes. And it's going to, this term is going to tend to homogenize the morph means, okay, across different morphs, and this is going to represent some directional selection that may move the morph means in different directions. For the variance, we have also equations. It's a bit more complicated. We have also three terms. One which represents like this homogenization process, like here. One which represents the effect of directional selection on the variance, and one which will capture more likely the effect of disruptive selection. The details are not very important, but it's just the fact that we can arrive to this kind of closed system using a Gaussian closure at the morph level is interesting. The problem is that it's a high-dimensional system. And so what we're going to do next is to try to reduce the dimension of the system, and that's where the repetitive values are useful, because we're going to aggregate the dynamics at the morph level. So we're going to average over all classes, but we're going to do this average in a certain way by weighting the morph distributions by something that is the product of these V quantities and these U quantities that I introduced before. And this product is called the class repetitive value in evolutionary biology. So we're going to use this weighted distribution. And it turns out that this weighted distribution will give a good approximation of the dynamics of the different distributions we are interested in. So what is the process? We have some morph decomposition. So for in each class, we decompose into distribution into two or more morphs, and then we aggregate our different morphs to obtain some aggregate morph distributions, and we're going to track the moments of these distributions. Yeah, I'll skip that. I think that is important here that we're going to recover separation of time scale with some fast variables, which are going to be the total density, the frequencies of the different morph in different classes, and this U and V variables, and then the slow variables, which are going to be the moments, the mean and the variance of this aggregate morph distribution. And then if we do that, we can really simplify the dynamics, because we have the fast variables will depend only on this aggregate, the morph means of the aggregate distribution. We'll have some quasi-equilibrium approximation for the morph frequencies U and the repetitive value, which are very similar to the classical theory we know in evolutionary ecology. And we have just for the slow variables, we have equations for the morph means and variance, which are again very similar to the equations we know monomorphic case, except that for the variance with an extra term that represents the interaction between the different morphs. Okay. If just a quick application to wrap up, if we take the very classical two-habitat migration selection model that I think was already addressed in this conference, where we have two habitats A and B coupled by migration. Okay, so this is, for instance, the transition from class A to class A depends on the fecundity in class A, and we have some migration rates from A to B and from B to A. Okay, this is a very symmetrical model. And then if we do that, we can have equations for the dynamics of the morph means and morph variance in terms of the reproductive values. Okay, and the derivatives of the fitness functions and the migration rates, and that's all. And it turns out that these reproductive values can be calculated using quasi-equilibrium approximation. And for instance, in the case of quadratic fitness function, which has been addressed in these papers previously, we have some very insightful expressions. Why is it insightful? Because first, the implication is that the morph mean stabilize when the morph mean reach the reproductive value of weighted optimum of each habitat. So there's a direct biological interpretation in terms of reproductive value. So if the quality of the habitat A is much larger than that of weighted B, we're going to converge towards the optimum of habitat A, and the reverse if the reverse happens. And also we have a very simple. Yep, I'm
sorry,
too long.
Okay, yeah.
So okay, I'm going to wrap up. I think I'm nearly done. Okay, just rapidly. So the selection of morph I is stabilizing if this condition holds, and that's interesting because that's a stability condition that depends again on reproductive value. Just quickly, we can also add the mutation term again with reproductive value weighted term, but this is just to show that it works. The approximation works well, but just to say that we're not limited to the selection term, we can also do the same with mutation under certain assumptions. And just final slide. If we extend to competition models, just to show that if we do it all the same, we'll see that here we'll see that the dynamics of morph means they depend on the means of the other morphs. So we really have some interdependence between the equations. So to conclude, well, I hope I managed to show that this method can be used to analyze the interplay of ecological and evolution dynamics over different timescales, especially the interplay between fast and slow evolution and in class structured population. And it kind of bridges the gap between dynamics and quantitative genetics to include some non-normal trade distribution, ecological feedbacks, non-zero standing variation, all these kind of limits that the two approaches have can be to some extent incorporated in that. Okay, so that's all. Joint work with Ryan, Mike, and thank you for your attention. Sorry, it was a bit fast, but first time I do this talk, so I talk too much there.
Yeah, thanks a lot for this interesting talk. Is there any question?
Hi, thank you, Sébastien. It's Jimmy Garnier speaking. So you said that you assume that the morph are Gaussian, and
yeah.
So what happens if they are not?
So if they're not Gaussian, then it's just that you have to track it depends how, but for instance, if you assume that you have a skewed distribution for each morph, then you'll have to take into account the third central moment of the morph distribution. So it's a bit more complicated. I think my idea is that often it won't be needed to assume that the morph distributions are skewed, for instance, or non-Gaussian, because what matters is that the overall distribution at the population level, we can model it as either a skewed or multimodal distribution. So how we model the morph, since anyway the morph are going to be assumed to be relatively narrow, is not so important. But in principle, you could do the same kind of equations, just you have to track more moments, so it's a bit more complicated.
Okay, thanks.
Okay.
So there's one question on Zoom. Leonard, if you want to take.
Yeah, I must have missed in the introduction. Are you talking about asexual or sexual populations?
Yeah, it's asexual populations.
Okay.
Everything is asexual, and it's nearly faithful clonal reproduction. In that case, there's just mutation regenerating diversity. So it would be very different if we were to have sexual reproductions or diploid noodles and so on. But yeah, you have to start somewhere.
Yeah, I guess so. Thanks.